How to build a better science project. Secondary science. This webinar is brought to you by your SISD science team. How to build a better science project. Section 1, picking a topic. Section 2, category. Section 3, experiment. Section 4, results and data. Section 5, real-life connection. Section 6, components of a project. And Section 7, tell your story. Picking a topic. There are many questions in the world without an answer. Often the hardest part of the science project is determining what question to ask. Questions for science projects should be relatable for the students, should apply to their lives or to the lives of the people around them. The main thing you should do is have students select a project that interests them. This is the number one thing that can change the mindset of a science project. On the internet, there are plenty of places to get ideas for science projects. Here are a couple. Thought.com, and this provides you with a list of science fair ideas by grade level. Now, the recommendation would be to start with your grade level. Have the students start with their grade level, kind of sift through some of the ideas there. If you have students that are that take to science and they enjoy science, perhaps you allow them to go up a grade level or 2 grade levels. If you have students that have struggled a little bit in science, this would give them the option to go down a couple levels in science. Another idea is through sciencebuddies.com. In sciencebuddies.com, they do have a topic selection wizard in which you fill out a survey. Student fills out a survey and is able to provide information, and Science Buddies provides you with suggestions for a science fair project. Now, it is my recommendation that even if you go through ThoughtCo or Science Buddies, that potentially you should be changing or altering the experiment to fit your to fit the student's needs. There have been times that we have come across science projects that are taken straight from Science Buddies, procedures, materials, everything exactly the same, and those science fair projects haven't fared as well. It's the science projects in which students alter whether variables or independent variable or dependent variable, or altering certain controls within a project. Those projects tend to do better in the long run. Ideally, what we'd like to have is students find questions from research that they've done on their own, from things that they've seen around their house, from family members, from ideas that family members have had. There are plenty of questions that could be based off of things that they've seen on TV or movies, or even through social media. These projects tend to be more personalized to the students and can mean a little bit more to them as they go through the process. However, some students may benefit from being provided a project topic in order to take that first step. On how comfortable your students are, you can have them choose from options on the internet, or they can ask their own questions. I know for me as a science teacher, providing students with topics allowed them to take that first step and to get going. And these are students that normally would have had a hard time with that first step. And even and in other cases, I would provide students with topics, and they would say, you know what, Mr. McDonald, thank you, but no thank you. I have a question that I want to answer for myself. It's also recommended that if a student has already done a project, they could, it's not necessarily game over for that project. They can continue that project, and plenty of questions arise during the process of creating a science project, additional questions that students can search answers for. So if students would like, they have the option of continuing projects from previous years. It would have to be identified if you were continuing a project in middle school, that it is a continuation, and you would have to provide information of what was studied the year before. But if you were moving from 5th to 6th grade, that is considered to be a brand new project, not necessarily a continuation, or the same thing happens from 8th grade to high school. But if you were going from 6th grade to 7th grade, it would be considered a continuation. You would have to provide the information from the previous year's study. Same thing would happen in high school as well. But it does give the students a chance at multiple years of research to build on their science project. That science projects are just like their favorite video game. They can always continue. Categories are another part of your science fair process. They can work a couple different ways. In secondary level, we have 21 categories, and these categories are based on the International Science and Engineering Fair categories. They determine which categories we fall into. So these are the same categories for high school and for middle school as well. The website for ISEF, or for the Society of Science, has these categories, and by clicking on it, it does include a description of the category. It will also provide you subcategories within each category, but we don't necessarily abide by the subcategories. Anything in that subcategory would fall into the higher category of the umbrella, the category umbrella that those subcategories would fall under. Now, not all categories are necessarily the same. We do have some popular categories, which include behavioral and social sciences, as well as physics and astronomy. Those tend to have the highest number of entries. And then we have categories that aren't as heavily populated. For example, computational biology and bioinformatics, as well as translational medical science. So each one of the categories has its own I guess following in a sense, and you can start a science project can start from either way. You could start with the question and place it into a category, or students potentially would have an interest in one of these 21 categories, and they can start to search for a topic. They can pick the category first and start to search for a question within a topic underneath that category. There are some things to consider when choosing your categories. For example, animal science, behavioral and social sciences, as well as microbiology, would have, if done using vertebrate animals or human subjects, or swabbing of unknown substances. For microbiology, they would require additional paperwork, and potentially with that additional paperwork, it would require working with a scientist, a certified scientist, so whether it be a veterinarian, or having access to a lab in a university, or having permission slips to work with human subjects, would be additional things that would have to be completed for a science project. Now, it's not to deter kids away from this. It's just to make sure that they are aware and that parents are aware that this could be a reality. So the one thing we want to avoid is having students go through the whole project process and then being told that, look, you should have done this project under the supervision of a trained scientist, or you should have done this experiment at a secure location that can handle certain situations if anything goes bad. With the animals, it's always ensuring that the animals are treated appropriately. They're not starved. They're not hurt. Checked for pain. Anything along those lines. Same thing would go for any human participants, ensuring that the project is not dangerous to any humans. That you're not messing with any bodily fluids or blood or anything of that nature. And the big one for the microbiology is the idea of swabbing unknown substances and coming across things that may not be healthy, especially in these times, post-pandemic. There's still uncertainty with certain things that we can come across. So any type of swabbing of unknown substances would require a scientist and a lab to work in. But there are some workarounds to some of these areas, and these could be recommendations to students who are dead set on these categories. Sea monkeys Sea monkeys are a type of brine shrimp that are not necessarily found in nature. They are kind of produced. Uh, they are specially bred for sale as pets. These are available at Amazon, probably under $20, but these are invertebrate animals which would not require the additional paperwork or supervision. So running experiments with these sea monkeys, they grow quickly. You could run day, night studies, put some in the dark, see how they change, different foods, things of that nature. Alternatives for human behavior and social sciences. If you were doing observational studies in which you are in a public setting watching human behavior, you would not need any paperwork from those participants. You were just watching generally a general group of people. So perhaps if you're at the mall and you're watching to see how many people cross your path and they're holding their cell phone, or maybe you're at a intersection and you're watching for the same thing, how many drivers are on the cell phone. These would not require any additional paperwork or human consent forms from those participants that you come across. As far as the bacteria, there is an option to purchase known bacteria, which known and safe bacteria, which which would allow you to work in at least the school setting. So whether it be the school lab, or your middle school lab, or your high school lab, and that way we know what is being worked with and that it is safe for students to work with this stuff. So just a couple of suggestions as far as how to stay in these categories, but to avoid the additional paperwork. Now, again, this is not to discourage kids. This is having students reach out to veterinarians and to explain their project, or to reach out to labs is a great part of the process of doing a science fair as well. They may need additional support from their coordinators, from their teachers, from their parents, to be able to reach out to these locations or these people, but it is a great part of the process. Experiment. In your experiment, you should have a set of variables that will be a part of the project. So there are 3 variables that a student must have. So in this case, you would have an independent variable, a control variable, and a dependent variable. The independent variable is the one thing that we're going to change. So there's only one thing that we will change in a project. We want to make sure that we are changing one thing and we are only looking at one thing. That way we can say with certainty that one change has caused the result that we've been given. The control variable are all the things that we're going to keep the same. So if we're doing a project with 2 different groups, we would keep the conditions the same for both groups, except for the one independent variable change that we would change in one group. In the experimental group, we would change one thing. But all other things, whether it be temperature, location, amount of sunlight, these would all be things that would be control variables. And then finally, you would have a dependent variable. And this is the thing that you're measuring. This is the thing that the students would want to see what was the result of changing this independent variable. And this is the thing that I can measure. So you could be measuring length, like suggested in the GIF here. You could be measuring mass, you could be measuring change in color, you could be change in behavior, different things that you could be measuring for your dependent variable. Again, one independent variable is changed. Control variables stay the same between experimental groups and control groups. And the dependent variable is the one thing that we are measuring. Enough data for a project, there has to be enough opportunity to put data together, to collect that data. So, but what does that mean for us? Well, every project should be done with multiple trials. The magic number for trials, and this is a trial, is every time you run the experiment, and it should be run the exact same way, same independent variable, same control variable, and same dependent variable, but it should be run multiple times. That magic number is 3. So we want to run at least 3 trials, and that should give us a efficient amount of data to come to a conclusion that our independent variable had an effect on the dependent variable. again, if you choose or opt to go for studies on plants or animals or humans test subjects, there is also a magic number in that. So if we're looking at test subjects, whether it be animals, humans, plants, the magic number for that is going to be 10. We want to have at least 10 test subjects. The reason for that is potentially we could have a flawed test subject, and for variables that we haven't considered, that may play a role in the results that we get. So, example, if I am doing an experiment on plants and I want to see if the amount of water affects the growth of a plant, but I have one plant that I'm giving a 1 cup of water to, and I'm giving another plant half a cup of water. If the results show that the half a cup of water, that plant grew faster, and the plant that I gave 1 cup of water to died, I could say that, well, the less water you give a plant, the more likely it is to grow. But what I didn't know was that my one plant that I had was already sick when I bought it. It was already dying when I bought it. So in order to combat that, you would buy 10 plants and have, or 20 plants, and you have 10 plants in one group, in your experimental group, and 10 plants in your control group, and that would give you a little bit more accurate information. So if you do have that one of the 10 plants in your experimental group dies, well, you can kind of forget that data and concentrate on the results of the other 9 plants. That data, what are you going to do with that data? So your data or your results should be collected and should be organized and into very easy to read graphs, tables, or charts. That way, as you start to present your information, it's a little bit easier to start to see trends or patterns within the data that you've collected. As you start to see those trends, this will become part of your conclusions, and that you would share with your teachers or your judges or whoever. But by being able to put this data into some graphs, it makes it a little bit easier to look at, as opposed to having a jumbled bunch of numbers on a piece of notebook paper. So gathering your data, collecting all the proper measurements that you want to collect, the dependent variable, and organizing that data into easy to read charts can help you spot those trends to help you draw a conclusion. Remember, these data tables and charts can be hand drawn using, but I would recommend using rulers, drawing straight lines, making it nice and neat. Or you can use any applications such as Excel to help create these as well. But either way, if you create them by hand or you create them using a computer program, make sure that you give yourself credit for making these. So you would have to put near the table somewhere, near the graph somewhere, created by researcher. Real life connections. So this is where good projects start to get separated from great projects. Now, with those students, what their job is to do is to consider, what does the data I collected mean for me and for the people around me and for the world around me. This is where students can start to really look to see what their research or how their research could affect the real world. So if we go back to our example of plants and water, if I find that this certain specific type of plant requires less water, then potentially this type of plant could be planted in drier areas, drier regions, to help prevent runoff, because they thrive with less amount of water. So if they are placed into an area with lower rainfall totals, then these plants could still do the job of maintaining runoff and preventing runoff while still living in a very arid region. So those are the connections that you would want students to start to make with the results of their science project. So this could kind of go back to the beginning where they are picking their topic, and potentially these are areas where these questions start to arise. Again, once students have started to make these connections, potentially more questions are coming up, are arising, which would lead back to that continuation process. And students could start to think for the next year's project, oh, well, I learned this in this year's project, but now I have 3 more questions or 2 more questions that I would like to research for next year's science projects. So the real life connection is a big part of science projects. Now, science board. Once we've collected the data, we've run our experiments, we have results, we've organized our results, we have to put together a science board. Now, in the past 2 years under COVID, we have altered what we've done, and we've used a virtual setting. We've created PowerPoints, but this year, beginning with our state competition, we students had to go back to the board. Having attended the International Science and Engineering Fair, all projects had a board. So a board still plays an important role in the science fair. So let's take a look at some of the components of the science project. So starting with your introduction. This is where you give a short origin or background of the question that's being asked. This should be the beginning of your story. Whether it was you were fishing with your dad and you had a question about the types of fish and that can be found in certain areas, and you wanted to know if pollution affects those fish, and you started the project idea, the question started there. You would want to tell that beginning of the story during your introduction. And the question, you would want to identify exactly the question that you are researching or trying to answer with your experiment. In your hypothesis, this is where you give your prediction or your educated guess on what the results of the project will be. Your materials are the list of materials that you would be using for your project, and these are normally presented a bulleted list of materials. So this would give you all the materials that you're going to use in your project. You would identify your controls and your variables, both independent variable. You want to make sure that it is stated that this is what I'm changing, and this is what I'm measuring, and this is what I'm keeping the same. After that, you would have your procedure. Now, your procedure is a numbered list of the steps that you followed for the project. Now, this becomes very important. This should be written in a cookbook type style, where more often than not, the first word in the sentence is a verb. This will allow your project to be recreated in the exact same manner that you tested it in, and potentially to check your results to see if it is recreated in the exact same way that you did, that you created it, if somebody else could achieve the same results. You would have a section for your data, or you could show a raw form of your data, maybe a table showing the collection of things. Also, you could include any graphs. But then the next section would be analysis or the interpretation of that data. So you would start to show those trends that you spotted as you created the graphs for your data. And then finally, you would make a conclusion. You would determine whether or not your hypothesis was supported or not supported by the data that you collected. Any explanations as to why or why not that data supported your hypothesis. And then any additional questions that arose during your experimental time, and potentially any mistakes that you found as you were going through the process. This is, a lot of students get hung up on this, but your hypothesis does not have to be right for your project to be a success. Mistakes are made, and this is part of the process as well. So as you go through things, sometimes things don't work, and that's all right. That's you note it, you keep a record of it, and you start to change the question or the approach you had to answer the question. A lot of kids assume that their data has to support their hypothesis or everything is wrong. Please convey to your students that that is not the case. Science happens through being wrong, through making mistakes, and it's a process. We do have a suggestion for a science board setup. This is your traditional trifold board, or on the left-hand side, my left-hand side facing the board, you would include your introduction. You would you would include your bulleted materials, and then you would include your numbered procedures, the steps that you took. In the center panel, you would have your title, your question, your hypothesis, and in your center title, you could also include your different variables, your independent variable, your control variable, and your dependent variable. This is also a great place for any data, your drawings, photos, graphs, charts. Remember, in your photos, it should be only photos of the researcher. If other people are included, they should have, our researcher should have collected written permission to use their faces in the project. On the right-hand panel would be your results. This is your raw version, maybe a table of the information that you collected. And then below that, you would have your conclusions. Now, in your conclusion, again, you are stating whether or not the hypothesis or hypothesis was supported or not supported by the data. And again, any mistakes or future implications for the project. This is not the only setup. This is the setup that we have chosen to use, but after visiting the International Science and Engineering Fair, I was able to bring back some pictures, and here are some different areas where you can see how the different projects were set up. The boards can vary. In this case, we have a double board. In this case, we have a single board. And I don't think this is a full double board. I think this is pieces are put together, but you can see the graphs being in the center. You can see questions, purpose being on the right-hand side. So sometimes the titles change. Purpose would be a change from the introduction. You have your question here, methodology, or some of your procedures. What did you use for it? Here we have a different type of board, which is everything was printed onto a screen, and this screen just drops down into this area, and now you have a very easy setup for your project. Here's some other additional examples. Color tends to be part of it, choosing the color, what is going to catch their eyes. You want a little bit of color, but not too much color. You can see the simplicity of the graphs in this project. This project was printed out and glued to a trifold board. You can see the pictures are pertinent. It's the information. It's very straightforward. It's not overwhelmed with different things. You can see in this example, there's plenty of information that is being provided. Again, you have another project where it is printed out in a large sheet and glued to the trifold board. In this case, the researcher also provided some images on the laptop, and that is the only thing that can be provided on the laptop. So there should be no internet connectivity. They shouldn't be relying on a YouTube video. This has to be on the laptop, no internet connection whatsoever. Yet another example, and you can see again the simplicity of the board. I think this could use, so there's a little more space that could have been used. They could have increased the size of their information. That's just my personal opinion. Again, here's another example where there was a lot of information included. Now, in this particular project, there were several steps, several experiments that were completed to answer their overall question, and they included every experiment that they went through, procedures and things of that nature to come to their full conclusion. By the way, these two young men did win a special award at the International Science and Engineering Fair. Here is an example. This young lady is from El Paso, and you can see that this is her board, very clean, very neat. All the required information is there. You can also see that she has additional information in data notebooks as well. And another example here. Tell your story. Finally, this is a big part of it. Your presentation, your board is going to tell a certain part of the story, but chances are a lot of your judges are not going to necessarily look at just the board. A big part of it is the student selling the story of their science project. Now, I call it a story, and it should be treated as a story because students should be excited about what they were able to find, what they created, what the research that they did. So it should be an exciting moment for the students to share all their findings with their classmates, with your teachers, with the judges. So the more they practice at the presentation, the more ease that the information comes out, the more excitement that comes out, the better way the judge can see that the student not only put this thing together, but they actually learned something from it and had a good time creating it. So a lot of the projects that I've seen, successful projects, the presentation is absolutely key. I have seen projects where the board is an absolute mess, but the charisma, the excitement of the presenter made the judge completely forget about the board, and the student is able to, receive awards for that project. If you can get a student who can do all parts, put all these components together, as far as the topic, the experiment, the gathering of the data, the organizing of the data, the putting together a clean board, and then giving a clean presentation on top of that, that is the recipe for a project that it will move on from the campus to the district to Sun Country Regional Fair and on to state, potentially on to the International Science and Engineering Fair, which should be the end goal for all our students. But it is that sale. It is that excitement about the project that is huge. Considerations. So in being a part of Science Fair for 10, 15 years now, I've seen plenty of projects. So the idea of our next level for our students is being able to reach out for help. Seeing what the projects were at the International Science Fair has been very eye-opening for me, and I think that process starts at middle school. So with our middle school coordinators, reaching out to our high school coordinators for help as far as the use of labs or any specific materials can benefit our middle school kids. A lot of times at the high schools, there are teachers who have their degrees in certain fields, who have done research as students who have been part of college science projects. This could be a great resource for our kiddos in order to clean up their projects and to put out a better product. As far as our high school kiddos, reaching out to their coordinators again, finding that mentor teacher on campus, or even next level stuff would be reaching out and finding mentor professors at the university level. So starting with EPCC, going on to UTEP, trying at Texas Tech. And now with the way that our world is, these mentors don't necessarily have to be in our town. They can get onto a Zoom meeting, a Teams meeting, and talk with their professor, but it would all start with the students reaching out to find that help. A lot of the students that I came across at the International Science and Engineering Fair had mentors. They worked with people at the college university level who do research for a living. I think this is this could be a big stepping stone for the kids in El Paso to continue to perform better at the state level, to continue to represent better at the international level. So this is my recommendation for our coordinators, for our middle school kids and for our high school kids, is to start to reach out. Once I was able this year to reach out to UTEP in not only UTEP, University of Texas, Texas Tech, Texas A&M, just kind of shotgunning emails to email addresses that I found on the internet, on the school websites, finding people in the specific categories and saying, excuse me, we have a couple projects that fall into your category. Would you mind taking a look and providing us with some feedback? And it could start as simple as that. They are busy people, but you won't know until you try. So this is our next step, and this will be my next push to improving SISD Science Fairs. I am providing you with some power tips that I found on a YouTube video created by the creator of the Glitter Bomb package, which students are very familiar with. It was a pretty cool series on a scientist, an NASA scientist, who was trying to prevent packages from being stolen, Amazon packages from being stolen from this porch. The link for this video will be provided in the Nearpod, as well as links to all the websites that I've talked about in this presentation. So the power tips that he provided were, number one, make it relatable. So making sure that that student has a connection to it, and that way, if the student has the connection to it, they could turn around, in turn, turn it around and make it relatable to any judges or teachers. A reminder to change one thing and measure one thing only, so having one independent variable and one dependent variable. The third thing is making a prediction based on an initial observation, so making that hypothesis based on some prior knowledge or a little bit of information that you've gathered in the initial observation. And finally, that interview practice. It's telling that story, making it relatable, telling the story in a captivating way to get the judges excited, just as excited as the student is about their research. Thank you for hanging out and listening to my webinar. This is Frank McDonald. If you need anything, please here's my contact information, and follow me at Twitter. Thank you.